Okay, so stoichiometry is basically looking at the equation, or not the equation, the question, how much of one chemical can I use to produce another chemical, or how much can I react with another chemical, or how much of it do I need in order to make it from another chemical? So going in all the different directions. So that sounds a little bit complicated, but we like to think of this in terms of a recipe. Now, we all know that you can kind of tweak recipes and you can throw in a little bit more salt or add an extra slice of cheese if that's what you like on your sandwich. But for chemistry purposes, we're going to pretend that our recipes are fixed, that you have to make them in a very particular way. You're not allowed to change those recipes. So if we think of a recipe for a s'more, I like 2 marshmallows. We're just going to use 1. Okay, so we build our s'more. We have our graham cracker, we have our chocolate, we have our roasted marshmallow and graham cracker on top. Very simple sandwich. So basic s'more. So what this is saying is that we could ask ourselves, how many marshmallows do I need to make 10 s'mores? Or I could ask myself, if I have 20 graham crackers, how many chocolate bars do I need to completely use up those graham crackers? Or I could ask myself, if I want to make 20 s'mores, how many marshmallows do I need to get? Okay, so I'm going camping and I know that there's going to be 10 people. They're each going to have 2 s'mores. I need to go and buy ingredients and I need to make sure I have enough of them. And so I got to make sure, do I have enough marshmallows in the bag? That's what stoichiometry is asking. Okay. So if you think of it in terms of a recipe, it's not as complicated as that word makes it sound to be. Okay. All of chemistry, the stoichiometry works in moles. And if you're going to do stoichiometry with an equation, the equation's got to be balanced. So I can't just say marshmallows, graham crackers, and chocolate bars, how many do I need? You have to know that you're going to need twice as many graham crackers as you do of the other things, or you're not going to buy enough graham crackers. Okay, so we have to have that balanced equation. So we're going to work with this one making ammonia. So NH3 is ammonia. Okay, and when we think of simple stoichiometry, we're just dealing with the moles. Okay, so we're just going to start here with moles, and then we're going to step back and say, hey, we know how to get to moles from other places. Okay, so first let's just deal with moles for a second. So I might think about, if I needed to make 100 of these ammonia molecules or ammonia moles, to make 100 moles, I need how much of the nitrogen? Well, 1 nitrogen molecule will give me 2 ammonia, right? So I have twice as many ammonias as I do nitrogens. Okay, so that tells me that this is going to be 50 moles. Or I might say, I have 66 moles of hydrogen, and I want to know from that 66, how many moles of nitrogen I'm going to need to react with it completely. So I have enough nitrogen to get a good reaction. So this is what I have, and then I'm going to need, this one's what I have. So I need how many moles of nitrogen? Well, I have 3 times as many hydrogens as nitrogens. Every 1 nitrogen, I need 3 hydrogens. So what am I going to have to do to this 66 to figure out what I need? Divide it by 3. So this is going to be 22 moles. All right, now it gets a little bit more complicated. Yeah.
Where did the 50 moles come from?
Because I said I wanted to make 100 moles of this.
Right.
So how many of this do I need to start with?
Is it because the...
It's because the ratio is 1 to 2.
Okay.
Okay. And so this is kind of getting to the point that I was going to get to with the next example, is that once you have things that aren't nice whole numbers, this can get a little confusing, and it's better to have a way to do this mathematically than just kind of being like, okay, twice as many, half as many, what am I doing here? Okay. So the example I was going to say is, okay, if I have 66 moles of hydrogen, what number of moles of ammonia am I going to get? Well, now I'm not just dividing by 3 or multiplying by 3. I've got numbers on both of these. And that gets a little bit harder to do in your head. Okay, so if you did your prepare to learn, then you will recognize this term. You may not know exactly what it means, but I told you to find what the term was. Stoichiometric factor. So what we're going to do is we're going to take the thing we know, this is what we have or what we want, and we're going to multiply it by a stoichiometric factor. That factor is what I sometimes will call the mole to mole ratio. Okay, how many moles of nitrogen are equal to how many moles of hydrogen? How many moles of ammonia are equal to how many moles of hydrogen? Okay, so the stoichiometric factor is going to be the coefficient of the unknown, the thing you want, divided by the coefficient of the known, the thing you have. I can do a lot of things. Spelling is not one of them. Okay, so I was asked a question. If I have 66 moles of hydrogen, and just for the sake of saying what we have, and 22 moles of nitrogen, so we know it's enough. We're more focused on the hydrogen, though. How many moles of ammonia can I make? Okay, so from my question, I was given 66 moles of hydrogen. So I'm going to take that. And when you're starting any sort of calculation in chemistry and you're trying to convert from one thing to another, it's best to start with something that only has one unit. So this is just moles. The factor or the ratio has two things. It has the coefficient of one and the coefficient of the other. If I have molarity, I have moles and I have liters. I have molar mass, I have grams, and I have moles. I don't want to start with those numbers because I don't know which way the ratio is going to go. So I'm going to start with a thing that I have just one unit. That's going to be the amount of stuff that is there. Okay, then it says multiply by the stoichiometric factor. That factor is going to be the coefficient of the unknown. So what we want is ammonia. So I'm going to put that on top. So I'm going to say 2 moles of NH3. So we always put moles with that stoichiometric factor. And then I'm going to divide by the coefficient of the known. So the known is the thing I already have. So a lot of times when we set this up, we say, well, what units do I already have? That's going to go on the bottom of my fraction. So I'm going to put 3 moles of hydrogen. So for a mole to mole ratio, that's all I have to do. I'm going to multiply it through, and I'm going to get 44. I'm canceling moles of hydrogen, and all that I'm left with is moles of ammonia. All right, so let's try a different equation. Let's take a look at propane. Now, we have different kinds of chemical reactions we're going to look at in this chapter. And one of them is a combustion reaction. We've seen a lot of these combustion reactions. Anytime you burn something with carbon in it, what we call an organic thing, we tend to get the same products. You may have noticed that over and over again, we were getting carbon dioxide and water. That's a combustion reaction or organic combustion reaction. So we're going to start with propane. If we're going to do any kind of stoichiometry, we need to balance this. So take a second, try and balance that on your own. All right, so do I need any different coefficient here, or is the invisible one fine? It's fine. I'm going to skip oxygen. What is this one going to be? 3. What's this one going to be? 4. And what is this one going to be? 5. I agree with that. Mason's doing a lot of talking. Anybody else agree with Mason? All right. All the Masons agree. And Robin. Okay, so let's ask ourselves this question. We're on an island, salt water all around us. We can't drink the salt water. That'll make us sick. But we have a tank of propane. And we're like, I know if I burn propane, I'm going to get some water. How much water can I get from 100 moles of propane? This probably is not the best way to get water, but we're going to give it a try. All right, so we're going to start with our known. That's the propane. We're going to multiply by our stoichiometric factor. On the bottom is going to go our known. On the top is going to go what we want, our unknown. And the numbers for a stoichiometric factor come from the balanced chemical equation. That's why we had to do that first. So what number is going to go on top? So we're going to take it from the water. What number is in front of the water?
4.
4. What number is going to go on the bottom? 1. So remember that if there's not a number, that's our invisible 1. We can feel free to write the 1 in when we're doing a factor. So basically we have 4 times as much water as we have propane. The tricky part is capturing that water after we burn the propane, because it's going to be in gaseous form. We've got to figure out how to trap it so we can drink it. There you go. Okay, so after fall break, you're going to be using stoichiometry with solutions, and we've just been talking about solutions. So we know how to find moles from solutions. So now we can turn this into, instead of a simple stoichiometry problem, we can turn this into a solution stoichiometry. For each solution, there are going to be 2 things, not just 1, because we're not going to start with moles. What we know about solutions generally is their molarity. So the known, we will know their molarity. And to get to moles, we need volume. For the unknown, we will have one of these. So we're going to try to get to is whichever one is missing. Remember that molarity is equal to moles divided by liters of solution, okay? And we want to be able to do that mole-to-mole ratio step. So the first step in any stoichiometry problem is to get to moles. And in solution stoichiometry, we're going to get to moles by multiplying molarity times what? I'm going to put volume and then a little L there for liters. Okay, so step 1 is convert your known information to moles. And for solutions in particular, moles is equal to molarity times volume. Tricky thing with solutions, though, is usually our volumes are in milliliters. So that might mean we also have to change milliliters to liters. Got to check that before we jump right in. Okay. Then our second step is going to be the simple stoichiometry. So that's multiplying our moles by our stoichiometric factor, or what I like to call the mole-to-mole ratio. And then our last step is going to depend on what's missing. We're going to find our unknown. So if what I want is the molarity, well, I've already got my equation there. But if what I want is the volume, then I'm going to have to say moles divided by volume. Okay, so a little bit of thinking and planning ahead involved here. We have to decide which calculation we're going to do when we get there. So we'll do one quick example here. One type of reaction we talked about was a combustion reaction where we were burning things in oxygen. Another one is a neutralization reaction. And that's where we have an acid and a base. So I know this is an acid because it's got an H out front. Anything with a hydroxide is a base. So if we've got that as our polyatomic ion, that's the base. They will always produce water and then the combination of the ions, which we call a salt. All right. Anybody know how to balance this? We don't have to find the charges. We can just do the elements. So how many hydrogens do I need? We have how many on the left side? Yes. Okay. Over here, we only have 2. So that means we've got that even odd conflict. So let's go ahead and multiply this by 2. That way we've got an even number over here. That changes our chlorine. Are we balanced on our chlorine? Yes. Okay. And over here we have 2 oxygens. So we only have 1 oxygen here. We only have 2 hydrogens. Okay. So if we have, what is the concentration? That's what we're looking for of HCl if 21.50 milliliters of CaOH2 with a concentration of 0.022 molar neutralizes. This is why it's important to know that it's a neutralization reaction, so we know what that word neutralizes means. That's just telling us that's this reaction. Neutralizes 15.00 milliliters of HCl. Okay, step 1, we are going to find moles of the known. Now we have information about both, but the known is the one we have 2 things. We have both of these for the known. So we are going to do 0.022 moles per liter. And we're going to multiply that by the volume. I'm just going to go ahead and convert that because we're short on time. But remember, we have to divide that by 1,000 to get to liters. And then when we plug that in, we should get 0.00473, which I can only do 47, yes, moles. I dropped my last digit because there's only 2 sig figs here. Okay, so I just put 2 sig figs there. So that's step 1. Step 2 is my simple stoichiometry. So I'm going to take my answer from step 1. Step 2, I'm going to do 0.0047 moles CaOH2 multiply by my stoichiometric factor on the bottom. Oh, we don't have time to finish this. I'm sorry, I ran over on time. We'll save that mystery for Monday. So you'll be with bated breath. You won't be able to wait. You'll have to do it tonight. You'll just go home and be like, what's the answer? You all come in raving, I know what the answer is.